So I'm John Wohlbier. I'm the Advanced Computing Lab lead in the AI division at the Carnegie Mellon University Software Engineering Institute. This is work that is 2 years out of 3 so far. One of these internally funded projects. It's called Co-Design for Edge AI, Application-Specific System on Chip. So what I'm going to do is talk about what SoCs are, System on Chip, Application-Specific System on Chip. I'm going to motivate some things by an application, and that is modulation recognition, like radio frequency modulation. We're going to talk about that application and things that pop out in that application that would that you'd like to make into an accelerator. I'll talk about what that means in a bit, how you integrate that, future work, and resources. So of course, on the left, edge devices such as drones are powered by microelectronics. Nobody's surprised by that. Examples include accelerometers, cameras, flight controllers, et cetera, and radios, which I have as transmit receive at the bottom there. So there's electronics there. What is the system on chip? Well, it's one of those chips. So we can pretend for the moment that it's that silver one right there. And it's a chip that contains components that comprise a system. So the kinds of components, and you can picture this on the lower left, that would appear in one of these SoCs are CPU cores, GPU cores, memory cores, or accelerators. I mentioned accelerators on the last slide. This is where I'll tell you what I mean by that. Accelerator is a dedicated piece of hardware for a particular part of your application. And so examples include fast Fourier transform, natural language processing. NVIDIA has an open source deep learning accelerator, and then all your radio hardware has this kind of specialized hardware as well. So why are we interested in this? Well, electronics efficiency plays a major role in system performance. There's a quote at the bottom that says, compute can improve mission time and lower energy consumption by as much as 5x. So it's a big deal. If you can tailor your hardware to match your software, you can increase mission time, increase average speed, et cetera, of a drone, that sort of thing. So what makes it the SoC application specific is when you design it for the system, you design the system components from the application. You start with your application that you know you have, and you analyze it, and you figure out what parts are in there, and what's the most expensive thing in terms of compute time or energy usage, and then you try to design specific parts for that. How do you do such design? There's lots of ways. The first one that I have listed there is something called hardware description language, and that's essentially writing software that makes circuits. So it's not software like you write in Python or something like that, but it's software that makes circuits. This turns out to be a very sort of hard to find resource. Not many of these kinds of people around, and it's very time intensive. It takes a lot of time to do this thing. You're going to get your best performance probably if you do that, but you're going to invest a lot of time to do that. So what you'd like to do is speed that process up, and so that's the next line there, high-level synthesis. So this means start from your high-level code and then see if you can automatically turn it into these specialized hardware components for your system. We have both of those activities in this project. Last year I gave this talk, a similar status talk, and we focused more on the high-level synthesis one. Today I'm going to talk a little bit about the first one, the hardware description language one. Lastly, once you have these accelerators that you've identified in your application, how do you make the system on chip? Well, for that, there's things called, there's frameworks such as ChipYard, and the one that we're using in this project is called Embedded Scalable Platforms. It comes out of Columbia University. Professor Luca Carloni is a friend of ours and a collaborator. So we got into this work through DARPA. So we do T&E, test and evaluation, for DARPA. And we were on the DARPA, and still are on the DARPA Domain-Specific System on Chip program. That's where the performers were doing this activity for their particular applications. And we got introduced to sort of all the technology across the entire thing, and we said, hey, we can do this. We can get a DoD application where they can't really, typically the performers can't do that. And we can try to apply these methodologies to the DoD application. So what's on the left is is what you want to think of when I talk about system on chip. You just got a square, basically. And then you make it, and you have tiles in that square. And in the tiles are where you're going to put your specialized stuff for your application. And so this is a real example of a real chip that was designed and taped out by IBM's during the DSOC program. And this is the specialized IP, intellectual property, that they put in their chip. So you can see you've got an I/O tile, you've got a tile that's for the natural language processing. The bigger block, the pinkish block, the Ariane, that's actually 4 RISC-V CPUs. So RISC-V is a open source ISA. It's becoming quite popular these days. Anyway, there's others. There's fast Fourier transforms and all sorts of stuff. And so that's what I want you to think about when I'm explaining what a system on chip is and what we're kind of doing here. But now I'm going to motivate it with a different application than the one that came on the slide before. This is the DoD workload that we have. We're collaborating with Johns Hopkins University APL. This is just sort of a cartoon picture and a high-level representation of the algorithm. And what it is it's in an edge environment, there's radio frequencies all around. And what you do is you want to know what those radio frequencies are, what kind of modulations they're using, and that sort of stuff. So they designed this workload to make sense of the detected signals. So that signal processing chain has lots of pieces to it. So coming in on the left, the first thing that the chain does is it tries to find if there's a multi-carrier frequency kind of situation going on. So OFDM is the most common, orthogonal frequency division multiplexing. If it detects one, it spits out something. If it's a single carrier signal, it goes on to this thing called SSCA. That's the strip spectral correlation algorithm, and that's what we're going to talk about most today. That determines a data rate, or estimates a data rate that's in the detected signal, and then it sends the signal into the machine learning piece, where the machine learning detects what kind of modulation is on the signal. So on the bottom there you see phase shift keying, amplitude phase shift keying, quadrature amplitude modulation, etc. So that's where the ML is. And the SSCA is really more of a traditional kind of digital signal processing application. It's really heavy on fast Fourier transforms. So what do you do when you have so we have this application, we have data, we can run it, and what do we want to do? We want to identify the hot spots of the application and figure out what pieces of it we should turn into this specialized accelerator IP. There are lots of methods for doing that. The traditional one is called profiling. You're just basically using tools to understand where time is spent, understand various things like arithmetic intensity, bandwidth, latency, those kinds of things. And then, of course, it helps to have expert knowledge of the application as well when you're trying to dissect this. So then you've determined what your hotspots are that you want to attack, and then you have these two accelerator design options that I talked about earlier, HDL and HLS, hardware description language, and high-level synthesis. Again, the HDL is time-consuming, but you can get optimal performance, whereas the HLS is much faster in terms of development time, like orders of magnitude faster in a lot of cases. But you're unlikely to get the optimal performance from the hardware. So there's this trade-off about how much time do you want to invest to get the thing. Sort of depends on how it's going to be used and how many you're going to make and all that kind of stuff. So I'm not going to talk too much today about high-level synthesis. If you want, you can go find last year's talk where I talk more about that and taking a PyTorch neural network and turning it into hardware. And I won't mention the other things. So let's get into, this is the math slide. This is the strip spectral correlation algorithm. And I'm introducing this because it's going to turn out that this is one of the things that we want to attack. And so what you have to know about it is, or you don't have to, what I'd like you to know about it is that this is some math to analyze what's called a cyclostationary process. And what a cyclostationary process is it's a signal having statistical properties that vary cyclically with time. What does all that mean? Well, so you have these high frequency carriers that are being modulated, And it's, the modulation rate is much slower than the carrier frequency rate. And so if that modulation rate sort of has this periodic behavior as at a slow pace on the high frequency carrier, that's going to tell you something about how the information has been encoded onto the waveform. The functions that you need to sort of do this analysis are the cyclic autocorrelation and the spectral correlation function, which are shown on the left. So the left is the cyclic autocorrelation. If you know what autocorrelation is, it looks very familiar. It's time shifted ahead and back and complex conjugate, because the radio signals are complex waveforms with the Fourier kernel there. So the alpha is the cyclic frequency. It's that slower frequency that if you can figure out what that is, you can determine like what rate people are putting onto the modulation. And then the SSEA estimates the spectral correlation function for all cyclical frequencies. So that's the bottom one. Alpha is is the slow frequency. F is the high frequency. And if you can compute that thing for given an X, you compute it for all Fs and all alphas, then you have new information about the waveform. So that's the end of the math. But I thought it was worth going through. Oh, and so I'm going to show you an example of what this looks like on the next slide for an 8 PSK signal. So 8 PSK is the thing on the upper right. So it's on the upper right, the symbol diagram, and on the lower right is like a waveform. And so basically you have this high frequency, and you're changing the phase of it at some slower rate to land on that circle. And then on that circle, in 8 PSK, you have 8 points, and you're going to call each one of those a bit of data. And so you got 0, 0, 0, 0, 0, 1, et cetera, et cetera. So that's what an 8 PSK waveform looks like. Well, if I put one of those through this SSCA algorithm, what do I get? And that turns out to be the stuff on the left. And the big spike is the data rate. So it's the rate at which I modulated the signal when I put it in. So SSCA did not have any a priori knowledge of what the data rate was, but it calculated it. The multiple graphs are sort of just showing that we have several implementations from MATLAB to the RTL to our reference application, just sort of showing that yes, we're doing all these calculations the same. So we want to profile this application. I maybe I should have had these in the reverse order, but we want to figure out where the time is spent in this application. So if you look on the lower left, you see not the bottom row, but the one up. You see 3 big chunks: scan, detect, and characterize. So what scan is doing is it's actually reading waveforms off the radio and storing the data and quantizing it and all that stuff. There's a first detect phase, which is essentially like figuring out what the noise floor is. And then the third and biggest phase is this characterization step. And the characterization step is split into 2. I'm not showing you all the information, but take my word for it. The SSCA thing that I just described is one of the big parts of this time, and the machine learning for modulation recognition is the other big part of this time. Just sort of an example of what you do, you can't really glean a whole lot from just this picture alone, but you can start to zoom in and look at the different pieces, and you start to see fast Fourier transform appearing everywhere. That's SSCA essentially. The other stuff, the machine learning is in the other ones, and then you see that the green plus, you would click that, and there's 194 more kernels that you could look at to figure out where all the time is. So this is just to show you, I have an application, I'm going to put it through this thing, and this is running on a NVIDIA Orin. This is a baseball-sized kind of GPU block. And this is NVIDIA Insight is the tool that gives you this information. All right, so hopefully I've convinced you that the SSCA is an important part of our modulation recognition application. It's FFT heavy, and we did this one by hand. This one was this is the hardware description language. And there's reasons to do it by hand and by high-level synthesis. If you do it by hand, or if you do it by high-level synthesis, you might never know what you are missing. If you did it, so you can't do it for everything you have, but once in a while you want to take one of these things, and it's sort of the spirit of this program or project is to understand that landscape of when I should do which one. So we synthesized that into a system on chip. That system on chip has a RISC-V CPU core, has a memory tile and an I/O tile, and we run it on, this is a field programmable gate array, the Xilinx VCU 118. And then we defined a benchmark to compare our reference application. So this was basically, we took our reference application and we pulled out the SSCA part and we made a benchmark around that. And then we ran it both on the NVIDIA Orin and we ran it on the FPGA. What you see in the bottom left are the results of that first run. So the reference application benchmark took 334 seconds. So this is like sifting through, I think it's about 200 megabytes of signal data maybe or something like that. And that's how long the Python running on the GPU in the Orin took. There's two different versions of the SSCA accelerator. One is where you have more FFTs in physical IP than others. And so the results are anywhere between 5 and 20 times acceleration. So that's a lot. And so if you can get 20 times acceleration, then you might think it's worth going through all this stuff that we've gone through to your application. This is just another picture. This one shows what's on the left is a list of Xilinx FPGAs, field programmable gate arrays, and then the numbers are the percent of utilization. And so, this workload is of a certain size. And it's not going to fit on everything. And so when there's a dark red, that means we've blown out of the resources, so we couldn't put our thing on that part. But the one that we're using, like I mentioned, is the 118. It's the 1, 2, 3, 4th row. And so we've got some space left. We're only using 36% of the LUTs, which are the lookup tables, and 25% of the registers, et cetera. I'm not going to go over the whole thing. But so this is another step of the process where you're figuring out which of these FPGAs am I going to target. So lastly, I'm going to talk about how we integrate it into a system on chip. So like I said earlier, we're using this tool called ESP, Embedded Scalable Platforms, from Columbia University. And what it looks like is this thing on the left. You see, okay, I want to make a system on chip. I run the program. It opens up this thing. It's kind of hard to read, but basically each one of these blocks there is a pull-down menu. So you get to pull down, you get to choose what you want to put in your system on chip. The red one is CPU. The blue one is a memory tile. The white one is an empty tile, and that's where we're going to put our SSCA accelerator. And there's all sorts of different kinds of parameters, including what kind of CPU core you want and that sort of thing. So that's a better view of it. So we pulled it down the menu, and then we picked. This is actually the slide from last year. So in that case, we picked the HLS for ML high-level synthesis accelerator. In the case that we're talking about today, your SSCA accelerator would appear in that spot, and then you would be ready to synthesize that. You'd also be ready to, if you wanted, and if you had enough resources and enough need, you could take this as a starting point of going to an ASIC. Actually taping out an ASIC, and this is something that we're going to pursue actually for our thing with campus. Ken Mai is our campus collaborator, and we've got this SSCA thing, and we've got the machine learning. We're going to actually take his class and try to tape out in theory, tape out a chip that does this. All right, so I think I'm almost done. This is just showing the setup in our lab. So the two pictures on the left are the FPGA board, the same board, just top view from on the right there. You can see they're connected up to there's a host computer off to the left that's not shown. They're connected by Ethernet, they're connected by UART, they're connected by JTAG, sent through a router to the host and sort of all the stuff. So the thing that you want to keep in mind is that this is a system on chip with a CPU. So it's a soft CPU, meaning that it's in FPGA programmable memory, but it's a system on chip. So you can SSH into that chip that's under the heat sink there. And so we've programmed that thing with our RISC-V CPU, with our SSCA accelerator, and we're going to boot Linux, and there it goes. And this is running at an accelerated rate, just for visual purposes. So it's booting, and then you log into it, and then you go to the application that you want to run, and then you run it, and it passes. Doesn't pass the first time, I can guarantee you. Takes a long time to get it passed, actually. Yeah, so that's sort of what it looks like. So that's kind of the status. We've just started our second year of the project. The goal is to have, by the end of the third and final year, a demonstration system where we're comparing this modulation recognition algorithm with IP for the SSCA accelerator and IP for the machine learning, and then do sort of like a head-to-head comparison against, this is a cartoon picture of the NVIDIA Orin that I mentioned earlier. It's like baseball size, kind of. And then also, as the stretch goal is to work with Ken Mai on campus and maybe tape out a ASIC that also does that. So there's a bunch of resources that are available. We have fundamental research on this project. We have 6.2 FR, and so a lot of the stuff we can put up there and share. And this is really critical for our ability to interact with campus in particular. Not only campus, but we also work with Penn State University Applied Research Lab on this as well. So there's a couple of different like Docker environments, but anytime we want to share anything with campus, this is the method. We can't take the code that we got from APL and actually give it to campus. It's controlled. And so we have to come up with proxies and all these kinds of things. So in principle, you can go reproduce all this work yourself. And let me know if you try and if you need any help. So I think that's all I have. I do want to mention, sort of like Linda did, we have this one connection with APL. We're looking for others who have, if this strikes your fancy and you have an application and a need, feel free to talk to me, and we could talk about doing it for your situation.